Okay, so my name is Hoa. Today I'll be talking about one of the engineering project that we're working on, on the 3D scaffolding cantilevers for potential AFM applications. And let me begin with this slide, where we basically, for any nanoscale metrology techniques, speed and reproducibility of high resolutions is always the goals. And it's also true for AFM applications where we have been pushing for high-speed AFM or large area scanning or wafer scale imaging. And for those one, as the fundamental or one of the most important components in AFM is the cantilevers. So it requires to have high resonant frequencies for high-speed AFM and also low spin constant generally for scanning in a large area. So if we go to the first one, the AFM cantilevers for the high-speed scanning, what is the range of frequencies? It's not clear here, but anyways, it's ranging from typically from 200 kilohertz up to a few megahertz. And high frequency is placed in a role that we can achieve a higher imaging time speed, and also we can also increase the response time of the cantilever. And what for high frequencies normally achieved by small cantilevers, we can have a typically lower level in noise. For spin constant, the values of spin constant ranging from 0.001 up to 30 Newton per meter, and this is the range of accessible values that right now that I have taken on the commercial AFM cantilevers. For the second applications for scanning in over a large area, we typically have seen and have probably experienced ourselves about the problem of tip wearing and damage. And this is just an example of one of that. When the longer we scanned, and then the more the tip get eroded. And as a result, AFM images we're losing resolution information, and also reproducibility of the system, since we have to change the cantilever once in a while. And the reasons for this to happen is that it could come from many different reasons, but the first commonly one is the tip engagement force, and the second one is the uncontrolled tip samples impact due to noises. And again, there's a number of sources that can cause noise. one of which is the noise caused by high resonant frequencies modes, because in non-contacting mode or tapping mode, the detecting system is only seeing the motion of the beam as with one fundamental frequencies, and the higher modes of frequencies is normally considered as noise. To solve this one is possible, but it's annoying too, and it requires a lot of efforts in electronics, and also to solve this one. And every single cycle of scanning, the tips will be contact with a substrate and create potential wearing problems. So let's have a look at how do we actually design and how do we make the cantilevers. This is the two equations represents for calculating the resonant frequencies and the spin constant for solid rectangular cantilevers. So we have first is the geometry of the cantilever, including the length, the width, and the thickness. Then we also have the intrinsic properties of material, including the Young Modulus and the density. So the first way to when we want to make higher frequencies or lower spin constant cantilevers is to make the cross-section smaller or thinner cantilever in this case. We're keeping the length as constant, so we can technically reduce the spin constant to a lower level, but at the cost of lower in resonant frequencies. So another approach is to make to not compensate a spin constant over to frequencies, is scaling the whole thing down, including the cross section and the length. So we're going up in higher frequencies, and all we can achieve smaller in spin constant. But at some point we reach the limit, and the fabrication limit, which I'm talking about is the length and the thickness here. And also, if we're making the width too small, then there will be challenges in optical detection system where we cannot focus on too narrow beam. Another way, of course, is to make the cantilevers by different materials. The most two common materials for using to make cantilevers is silicon and silicon nitride. And we can also use different materials to increase the frequencies up to, like, for example, diamond here. But again, at the cost of like a higher spin constant. So at this point, when we have reached the limit of length and the physical geometry of the cantilevers, and also there's not that many options from the material point of view. So what could we do now? There's one potential concept of metamaterials where we have researchers have demonstrated like ultra strong like strength against compression, and in this case, for example, it also exhibits elastic deformation. Another example. Another example is also a block of metamaterials, but instead they have like put into this block for 8 different crystal microstructures, so that we can have even more like higher strength against compression. So if we're looking at the micro scale, we still have the same materials with the same like Young modulus and density. But we're zooming out to the device level. We have an effective Young modulus and density. And one of the figures of merits of metamaterials is the ratio between them. And it's normally we're aiming for a higher ratio between Young modulus and density. So taking the idea of metamaterials and applying to AFM cantilevers, if we see if we can improve it. So this plot showing basically the 3 different lines called like limit lines. If we're reaching, for example, a length of 10 micron and the width of 2 micron and the thickness of 100 nanometers. So this is like the accessible range if we consider like making the cantilever as one solid piece of block. And so applying the metamaterials concept, we hopefully can break this boundary and access to like a forbidden regions. So we can gain technically both in spin constant and frequencies. So the ideas behind that is we have this come up with this design so that we're aiming for like a lower Young modulus for a lower spin constant, but higher ratio between like a Young modulus and density for higher frequencies. So to fabricate this one, I'm going to go quickly through this one. So there are the 6-main steps. So we're starting first with an SY wafer. We deposit a silicon oxide layer, perform photolithography, and then we etch the KOH etching to roughly about 200 or 300 nanometers. And then we do like e-beam lithography to define the tip, and then etch down to create a tip. And then doing e-beam lithography again to pattern like the beam structures. And then etch away, and then etch to create like the beam structure itself. And then we etch away from the backside to release the substrate, and then release the whole thing out by like a vapor HF etching. So we're right now at step 4, where we have just etched and created the structures, and this is how it looks from a 3-dimensional view, and also a picture from the cross-sectional view. But today I'm not going to go to focus on the fabrication, but instead we'll go more into like the design investigation and how these parameters can play a role into how do we design and get the optimal design of this particular cantilever. So there are quite a few of parameters to play around, including the length and number of bridges, and like the cantilever width and height, and also like the beam width and height for each individual beam here. And these are like all the possible cases that we have simulated, ranging from the cantilevers with a length of 100 micron up to and down to 10 micron. Let's have a look into each parameters. The first one we looked at is the beam aspect ratio. It's actually the aspect ratio of each one of beam here. So this aspect ratio, it affects the oscillation directions. So for AFM scanning, we technically want to have the vertical oscillation. But if we change the aspect ratio from, for example, to 0.25, we technically have like the Asian vectors going in like to the left here, for example, and in the other case, we go into the right. But because looking at like the aspect ratio is here from 0.5 to 2, we normally so we can say that the fabrication variations could not. Hopefully, we will not playing like a big role here, since we have still like a really small angles of the vectors here. Then the next parameters is the number of bridges. So as expected, when we're changing like the number of bridges from 2 to 20, it's technically making the cantilever stiffer. So we have higher in frequencies, but again, at the same time we have achieved like a lower values in spin constant. And then we adapt one with bridges of 10 bridges, and then we add in like to change the width of the beam from 100 nanometers up to 250 nanometers. So again, we have with the increasing width of the beam, we again make like the cantilever stiffer. So we ended up with like higher frequencies but lower spin constant. And about the width of like the cantilever itself. So we're starting with 3 micron here, and then for 2 micron we go into like softer regions where we have lower in spin constant. For 4, 5, and 6 micron wide cantilevers, we are going to like the regions of higher spin constant and lower in frequencies. And taking a look at this graph again, like showing the limits of the rectangular solid beam. So and then this is showing on a possible case of 10 micron cantilevers. So the first things noticed here that we reached the limit here, and then we actually can push and go out of the boundaries to achieve like either higher frequencies or like lower spin constant. Another thing is a comparison between the possible cases and the commercial high-speed AFM cantilevers, where normally it has the high resonant frequencies and relatively like low in spin constant. So take one example here. With the same frequencies, we can reduce the spin constant significantly, up to like 850 times more, like a lower in spin constant. And it's the same for like a long cantilevers of 100 micron long, and we can achieve like 2 or 3 orders of magnitudes lower in spin constant. In just this case here, this particular design, with the frequency around 300 kilohertz, we achieve also like really low spin constant. This particular design could be potentially useful for like both a dual mode of contact and non-contact scanning. So we selected these devices for like to go for fabrication. So we're talking about like I was talking about metamaterials, and then I calculate the effective Young modulus and density ratio between them, and we have like a 10 times higher in this ratio, the effective ratio, comparing to the bulk silicon. So we also excited to test this one and see how it performs in the lab. And for future development, so what we did before, like in this study, is technically find the best way to remove the mass, or like to make the cantilever lighter, but without changing too much the Young modulus. So right now we're testing other approaches if we can further improve the properties or the quality of the cantilevers. So one of which is to remove from the top an inner block of materials, so that we have a lighter cantilevers. So for example here, the graph showing like we end up with a number of blocks removed from 0, which is the solid beam, then 3, 5, 7, and 10. So for example, a number of 5 blocks removed, we have higher, almost double in frequencies, and also in lower in spin constant. So we're actually moving in both in a good way, and then we can decouple them and improve them both at the same time. Yep, with that I want to thank my group here and also to you guys for your attention, and I would be happy to take any questions if you might have one.
Yeah. Any questions?
Yep.
I have a question about the beam size. So it's when you use the electron beam to pattern the
Yes.
straw size?
I mean, that's just an extreme case if we want to make a really thin one, like for example 50 nanometers in a diameter or like in width. For the bigger one, we can still use like a direct laser writing and then string down using oxidation.
Yeah, we actually want to. So your case is you're trying to go to the extreme, right? So you're trying to make it as thin as light as possible. So I think there's another factor we should maybe consider, because the tip is oscillating all the way.
Yeah.
So there should be. I'm not sure. Okay, I mean, there may be a kind of fatigue associated with this. Maybe after some time, it's kind of.
Yeah, definitely like
maybe optimal number, and say not too small.
Yeah, like we haven't done really like mechanical properties studies to check if like this one is sufficiently strong, but yeah, I think that's one of the good like point to remember.
Very interesting.
Yeah, thank you.
If not, let's thank our speakers.
Yeah.